Chapter 4, Circuits. In this chapter, we're going to begin to apply many of the principles that we have looked at in chapters 1, 2, and 3. Introduction. There are only 4 basic ways to interconnect the various components in an electrical circuit, and the subject matter of chapter 4 is going to be those 4 basic ways. You must be able to analyze circuits to determine the expected values of the circuit. You must be able to apply the principles of basic electronics to account for differences between expected values and measured values in a circuit. So this chapter begins with 4.1, basic requirements for current. So before we look at the circuits, we're going to be looking at some of the basic requirements for current. The term current flow refers to, and notice this term, sustained current flow. Momentary or transient currents will be considered later in this text. There are 2 basic requirements for current flow. Number 1, there must be a source of EMF, and we talked about that in previous chapters. That was electromotive force. And number 2, there must be a complete path for current. EMF. EMF is difference of potential that does not decay as charges are transferred. And here we have a battery and an electronic circuit, and the battery is our source of EMF. Now, many comparisons are made between hydraulic systems and EMF, and there is a they do compare. Here is a hydraulic system, and here is a this would be the pump in the hydraulic systems, and hydraulic systems, the pump is comparable to EMF because it provides the pressure in the system, and the battery is the difference of potential, provides the pressure that actually induces current to flow through the circuit. In the hydraulic system, fluid flows through the system, and the fluid actually does the work. In the case of electronics, the current does the work. And in a hydraulic system, if there was a break in the pipes, then the system simply won't work. And the same in the case of electrical systems. If there is a break in the circuit, or the wires break, the current will cease to flow, and the work will cease to be done. So EMF is a potential difference that does not decay as charges are transferred. Electromotive force may be supplied either by, and usually a couple different sources, batteries or from a power supply. Ohm's law describes current flow in a circuit as current equals voltage divided by resistance. If there is no EMF in a circuit, the current will be 0. So if this is 0, then it doesn't make any, the current will also be 0. So there must be EMF for there to be current flow. The second requirement for current flow is a closed loop between 2 terminals of the EMF. So here we have this battery is representing our EMF, and here is the terminal 1. Here we have both 2 terminals, and there must be a closed circuit between these 2 terminals. For most purposes, an open circuit is considered to have an infinite resistance. So if you have an open circuit, you're looking at infinite resistance, and current will not flow well through that. An open in any circuit will result in 0 current flow. And I have a question here, does this circuit represent a closed loop? And quite obviously it does not. In this particular situation, there will be no current flow. This is like the hydraulic system where the pipes cut. So we could make this a complete circuit quite easily. We could go in here and draw a connection, and now we can have electron flow through this circuit, and we can have a complete path, and we can do work. Okay, direction of current. We're going to be looking at electron flow. Electron current flows from negative to positive, since electrons are negatively charged particles. And so the way we're going to depict this is here we have we'll start off in item A here, and we see a common line which we could understand to be ground, and then we have three voltage supplies, in this case minus 5 volts, positive 5 volts, and positive 10 volts. If we were to connect a resistor in this circuit, and let's connect to the ground, and we'll go to the positive 5 volt line. Now in this scenario, remember current, electron flow, current flows from the negative to the more positive terminal. So common is, we consider that to be 0 volts. So from 0 to positive 5 is going to be more positive, so the current flow will flow through the resistor in this direction, and this will be the direction of current flow. Now in this scenario down here, we're still connected to the common line, but we've connected to minus 5 volts. And so now this represents the more negative of the two connection points, because it's negative 5 volts, it's below 0. So now the direction of our current flow is going to be in the direction of the arrow like this. In item D here, we're looking at, and now in this case we're not using the ground at all. What we have is two voltages, and we're going to be looking at what is more negative, and this is going to be in a relative sense. Now in this case, positive 5 volts is more negative than positive 10. So again, current flows from the negative to the more positive. So in this case, the current flow through this component will be in this direction. Now in each of these cases, if this resistor is the same value, we're going to have the same amount of current flowing through each component here, and we would actually have the same power dissipated, but the voltage is slightly, here it's a positive 5, here it's a negative 5, and here it's a positive 5, but at any rate it's 5 volts, and through a given component it will give the same current and it will yield the same power. Okay, this is the first part of chapter 4. And the two main things that we looked at were the requirements for current flow in a circuit, and they are an EMF and a complete path for current.